All right. Hello, everyone. Welcome back to the last talk in our focus session on fractional inverse problems. Today's speaker is Professor Barbara Kaltenbacher, an Austrian mathematician. The main emphasis of her research lies in inverse problems and their regularization, where she has co-authored 3 monographs and contributed more than 100 journal papers. As this also involves modeling, analysis, and numerics of the corresponding forward problems, she got involved in several application-related topics, such as piezoelectricity, hysteresis in magnetics and ferroelectrics, as well as nonlinear acoustics, where the latter has recently become another focus of her research, with a monograph co-authorship and more than 30 journal papers so far. Her main achievements in regularization theory are on iterative regularization of nonlinear problems in Hilbert and also in general Banach spaces, as well as their efficient and stable implementation using and further developing modern techniques from numerics of PDEs and optimization. Concerning nonlinear acoustics, she has contributed to the analysis of classical and also advanced models. This research has been supported by the Austrian and the German science foundations, as well as by industrial partners in a number of projects, but among others provided funding for the 15 PhD students whom she supervised thus far. Her title today is Coefficient Identification in a Space-Fractional Equation with Abel-type Operators. Please, the floor is yours.
So thanks a lot for your kind introduction. I hope you can hear me well. Is this okay?
Yes, the sound is fine.
Okay, great. Thanks a lot for having me here. Thanks a lot for attending, and thanks a lot for your kind introduction. So the work that I'm going to report about today is from a joint paper with Bill Randell from Texas A&M University. And let me start with the problem setting. So we are looking at, so this is first of all the classical inverse potential problem in 2 space dimensions, x and y, and they will play distinguished roles actually in the following. So what we want to identify is such a potential, a coefficient, q, in this, let's say, Schrödinger equation. And we have boundary conditions, clearly. So it's an elliptic PDE. So we need boundary conditions, say, directly boundary conditions. But you see over there, we have an additional Neumann boundary condition. So it's the normal derivative. Since it's in this geometrical setting, it's just the x derivative here, negative x to be more precise. And what we want to seek from this additional information that we have along the y dimension is to recover q as a function of x. So, of course, we would not be able to uniquely determine q as a function of x and y from this setting, but note that our observations are in the y direction, and we recover q in the x direction. So to say, orthogonal directions in space, and this will give rise to severe ill-postness of that inverse problem. So we are given all these boundary conditions. So for simplicity, homogeneous, we will also put something else up there later on, and also directly boundary conditions, possibly non-homogeneous on the rest of the boundary. Then this overposed data G, but we can only measure it, so it might be contaminated with noise. That would be the typical setting. And from this overposed data, we hope to be able to recover q as a function of x. Now, that's the classical setting, no fractional derivatives yet. If we now look into fractionally differentiating, then instead of the elliptic differential operator that we had before, instead of the Laplace operator, we might have just fractional derivatives either in x direction or in y direction. So the case from before would arise by setting alpha equal to 2, obviously, but we are particularly interested in what happens if alpha is smaller than 2, and to what extent the non-locality that arises from this changes the nature of the inverse problem. So still we have our overposed data, and the inverse problem stays to recover this q of x here or here from this overposed data, G delta of y. So the delta up here is just to indicate that there might be noise in the data, as you will see later on in the numerical reconstructions. So I don't need to tell this audience too much about fractional derivatives. Maybe it's rather the other way around, but still, just to set the stage and introduce my notation that I'm using here. So first of all, it's about fractional integrals, and then how to make fractional derivatives out of them. There's several ways, and we will particularly look into two of them. One of them is the Chebyshev-Caputo derivative, which is obtained, so of order alpha between 1 and 2, which is obtained by just taking the second derivative, for example, here in x direction, and then doing a 2 minus alpha integral on top of this. Or another setting that we are also going to look at is a raised derivative, namely a symmetric one. And here we have some Riemann-Liouville type derivatives, because now you see the derivative is outside. So first comes integration and then differentiation. That's why it's Riemann-Liouville type. But in particular, the way it's written here, this raised derivative gives us a symmetric operator, which will be important later on. Just to give you an impression of how this inverse problem works, let's look at some reconstructions that we obtained by applying Newton's method to the inverse problem. So, and what you see here, I mentioned ill-postedness. So, of course, it's interesting to see how the several ingredients of our problem influence the degree of ill-postedness. In any case, you see a logarithmic scale here, and what you also see here, these curves here, these are the singular values of the linearization of the forward operator. So if you have an inverse problem, it's always a forward operator that we want to invert. In this case, it's a nonlinear forward operator. In order to assess the ill-postedness of the inverse problem, we linearize, and then we look at the singular values of this linearized forward operator, and this gives us an indication, the decay of these singular values and their smallness gives us an indication on how ill-posed the inverse problem is. Because for solving the inverse problem, one would basically divide by these singular values. So you see here, it's on a log scale, and it's sort of linear on this logarithmic scale. This means that the singular values decay exponentially in any case. Also, both for the integer problem, where it's known to be the case, and for the fractional derivative case. What one can also see is that if one takes weaker derivatives, so to speak, then the inverse problem becomes less ill-posed. And also it makes a difference on whether so let's go back to the setting maybe a bit, whether we do our additional observations, the G of y observations on the left-hand boundary, where also the DC derivative starts, where it's anchored, or whether we keep the DC derivative anchored at its side and observe on the other hand, to put our Neumann data on the other hand. Due to the non-locality and the connection between this initial point, in this case the left-hand endpoint, and the rest of the domain, due to this integral operator here, it makes a difference for the inverse problem. And this is visible here, in particular for values of alpha that are far away from 2. Of course, for alpha equal to 2, it does not make a difference, because then it's just a local derivative. But for small alpha close to 1, actually even, what we observe is that if we anchor the derivative at the left-hand endpoint and also measure there, then, well, it is a bit less ill-posed, because the line for the small alpha is above the one for the larger alpha. But over here, if we do it with anchoring still the derivative on the left-hand side, but doing this observation on the right-hand side, the curves become flatter. And this means singular values decay less quickly. They are still exponential, but not that awful anymore. And it means that this inversion problem becomes less ill-posed, slightly ill-posed. The intuition behind this is that, well, if we anchor the derivative on the left-hand side, oh, I shouldn't put it here. If we anchor the derivative on the left-hand side, measure on the other side, then we sort of make full use of the memory that this derivative contains. So the observations that we take basically take into account the whole line between the left and the right-hand endpoint, and this makes the problem better posed. It, of course, not well posed and actually still severely ill posed, but slightly less ill posed. That's the message from this. So here are some reconstructions. What I would like to show you here is still we have a dc derivative in x direction, and the dc derivative starts at the left endpoint. Here I can really point. So here's where we measure, and here is also where the dc derivative starts off. Both here and here in the upper and lower. The right-hand column, that's images where we still anchor the dc derivative at the point 0, but we do our additional observation on the right-hand endpoint. And so the upper row is without noise, the lower row is with noise. So it's actually with just 0.1% noise, but that's already pretty much for such a severely ill-posed problem. So let's first of all look at the upper row. And you see, of course, one consequence of where we take the measurements is, of course, close to the measurements, we get a better reconstruction. That's here and over here, respectively. What makes the right picture look, at least in my view, a bit worse than the left-hand picture here in this special case is not this memory effect, because this would go in the other direction. This would be in favor of this one. But it's the fact that, so to speak, this smaller bump over here is in the shade of the larger one. So we'll see a bit less of it looking from this side intuitively. With noise, however, the picture is slightly different, because as soon as we have noise in the data, stability plays a more important role. And we have seen from the singular values that stability is better with measuring on the right-hand endpoint, so opposite of the starting point of DC derivative. And you see really here, there's, well, it's really not so nice. Okay. So here are some further reconstructions. By the way, also the length, so this is this capital L of the interval. Let's look at the geometry back. The length of the interval in y direction plays a role, so it has an influence on the well-posedness or ill-posedness of the inverse problem, because if L is larger, then we have a longer interval of measurements over here, and of course, clearly this is better for the inverse problem. So with a larger L, also the singular values look differently. I don't show them here. This is now with the symmetric fractional derivative, still in x direction, so in horizontal direction. And so yes, this is already with noise, and you see some improvement as compared to the previous noisy picture, for example, here or here. Of course, with noise, now it does not really matter much on which side we measure, not with noise, with Rie's derivative, because it's symmetric, it doesn't favor one of the two sides, and actually takes information from both sides. And this is also what is visible here. Okay, yet another Rie's derivative case, but now in y direction. And now really we have an integer derivative in x direction, so the second x derivative. And you see from the reconstruction that actually this derivative in x direction, it is what is probably responsible for the ill-postness, which dominates the ill-postness because the pictures are now worse than before. Now, just for completeness, a mixed race derivative. So both in x and in y direction, we have a fractional symmetric derivative. And you see, as compared to the previous slide, we see a clear improvement. Of course, in particular, since we are measuring on this side here, but also over here. Okay, just to give you a rough impression. Now a bit more into the analysis of this problem. And first of all, I would like to dwell a bit about the question of uniqueness. The question whether the potential Q of x can be uniquely determined from the observations G of y. So here's the problem, and we first of all look at a uniqueness result in the case that we have a fractional derivative in y direction, either dc or res. So it doesn't matter whether we have a symmetric or non-symmetric. In that case, one can actually prove uniqueness of Q of x in this potential equation. It looks like this. Yes, we have the fractional one in y direction from these additional observations in y direction. So here's here it's slightly more general. We have some sort of driving Dirichlet boundary condition here, and instead the boundary conditions on these lateral boundaries are homogeneous, and they are slightly generalized to being impedance boundary conditions, just to show we don't need to vary these impedance conditions, but it's just to show that it works with these impedance conditions. Okay. Now how to get uniqueness. So our goal is to show that this G of y uniquely determines Q of x. Okay, in order to attack this problem, the strategy is to make use of geometry here, namely of simplicity of the geometry, in the sense that we really have these two orthogonal directions, x and y, and also our domain is just a box, a rectangle, actually. This allows us to do a separation of variables approach, namely in xy direction. So what we use is we take this Laplace in x direction and put it together with this Q of x times identity or Q of x multiplication operator. These two things together give us a second order space derivative operator in one dimension, namely in x direction, along with the corresponding boundary conditions. So we can just pick them out. And then we don't know Q, but what we know is that for a well-behaved potential Q, basically L infinity and non-negative, but it's actually, there's also, one can even do it with just an L2 potential that is not too far away from a non-negative L infinity potential. There is an eigensystem of this problem here, and we can use this eigensystem in order to sort of replace this elliptic operator with just multiplication with that eigenfunction. Or in other words, we do a separation of variables ansatz for our function u, for our PDE solution with boundary conditions up here. So in x direction, we use these eigenfunctions here in the ansatz. In y direction, well, we have to use functions that have to be tuned in such a way that after all the u satisfies the thing up there. But it's actually easy to write down what these w's functions have to satisfy. Yes, the usual thing that one does with separation of variables. Once we have these psi j functions in x direction, instead of this minus dxx plus q times, we just have multiplication with the eigenvalue mu j. And therefore, we end up with just an ODE in y direction. And it's actually a two-point boundary value problem for the ODE. because of course we should also satisfy the boundary conditions. Okay, it's now these boundary conditions at 0 and L in y direction. And in order to so we multiply with the coefficients of, okay, what's going on here? Okay, thank you, that's okay. Sorry, just Zoom popped up. Okay, in order to take into account this boundary condition, we have the corresponding coefficient with respect to the eigenfunction multiplied by unity. That's this unity over here. And that's how we get to a solution. Okay, still a lot of things are unknown here, but at least we know that they exist and we can work with them. So what is known is the boundary data. So we are going to go ahead and plug in the boundary points. So set x equal to 0. First of all, take the derivative, of course. Take the derivative with respect to x, and then plug in 0. And this gives us g of y, okay? Because g of y is ux of 0 and y. That's just this formula up here, inserted. And then we can even go ahead and look at what d alpha of g is, because just from up here, we can use this identity up here to express the alpha derivative of wj in terms of, or actually this wj here, each of these wj's in terms of mu j times wj. That's what is done here with a minus in front. And then we also get an explicit expression for the alpha derivative of g. Okay, the left-hand side is known, this is known, and this is known because we can differentiate in tangential direction, we can differentiate our data, maybe after some filtering to make the differentiation stable, but it's something which in principle we know. So here it's repeated. So this tells us that we know, we know this sum here, and, okay, sorry. It says that my screen sharing is paused. What did I?
I can still see your screen.
You can see my screen. Okay, that's fine. Yes, maybe I have been clicking around too much. Now, okay. Okay. It's hiding part of my screen. Oh, okay, like this.
Can you try to go to the previous slide and back again, just in case?
Yes, maybe, okay. No, it doesn't help. No. Is it okay? Most important that you
Well, I can see only the slide with equation 1. That's why I wondered if it's frozen, like, does it still work if you go back?
Does it proceed?
No, I can only see this equation 1.
Okay, then it says it has paused. And how do I'm sorry, it could be that I have to, I don't know how to remove this. It says your screen sharing is paused. Maybe I just
can you unshare and then share again?
Yes, I will do that.
Yeah.
Sorry for that. Now you see my screen again, yes?
Yes. Can you just try to go back and forth and see if it changes? Yes, now it's changing.
Okay, yes. Okay, we want to go forward with our proof because, well, we do know some things. We know the g and its derivative, so the left-hand sides. We also know the HAs because they are just the coefficients of this boundary data, A of x. But we don't really know these mu j's because they are eigenvalues of an operator that contains the q. We also don't know the psi j's or psi j prime because they are eigenfunctions. But so the next step will be to get from this whole sum to really filter, first of all, filter out this psi j information and the mu j information, and then proceed to really identifying them. First of all, to pick them out of the sum, so to speak, what we are going to do is to apply a dual basis. So for this purpose, we just note, and it can be shown in a small lemma, that these WJs that are actually defined as solutions of this 2.1D elliptic boundary value problem, that they are linearly independent. So as soon as they are linearly independent, there's what is called a dual basis, or actually it's a dual system because it doesn't necessarily need to span the whole space. But the important property is that applying elements of this dual basis to original functions W gives us the Kronecker delta, so 0, 1, depending on whether I and J coincide or not. Okay, then we apply these WJ stars to both of these identities. And due to this Kronecker delta thing, 0, 1, clearly both sums collapse to single terms. And they are just those terms that are left over after putting WJ to being either 0 or 1, after taking basically taking inner products, because it's anyway just L2. Okay, so then we have so to say removed the sums. We also know these WJs because so at least they exist, and therefore what we have gathered as information is this psi j prime of 0, so the values of the eigenfunctions at the left-hand endpoint, and also in a combination the eigenvalues, so eigenfunctions and eigenvalues and eigenfunction endpoints. For this to be really there, we need all these components aj to be non-zero, but this can be achieved, for example, by exciting the system with a delta pulse. Then for sure the inner product of A with any, so there should not be a J, it's just A here, so A of X should be delta 0 of X, then these inner products will be non-zero for all J. So now that means we have recovered the eigenvalues and the eigenfunction endpoint values at one endpoint. And now we can just apply Sturm-Liouville. Actually, it has Sturm-Liouville theory, which tells us, can be looked up in this nice book here, or in this more recent nice book by my co-author, that if we have the same spectral values mu j and eigenfunction boundary values, then the corresponding potentials have to coincide. So this spectral data uniquely determines the potential. And with this, we have actually proven this uniqueness theorem, namely that the observations G of y in this elliptic boundary value problem uniquely determine the coefficient Q of x. The only thing that we have to make sure here is that in our excitation, on our boundary excitation here, all the coefficients with the eigenfunctions are non-zero. The eigenfunctions themselves are not known, so it's not a condition that can be explicitly checked, but there's ways to choose a such that this set is satisfied. Okay, now, so this was about the y direction, and it's either dc or Ries fractional derivative in y direction. Now we would also like to obtain a uniqueness result in the case that we have the fractional derivative in horizontal direction. And we don't have this result. That's why it here only says on uniqueness. But this is just supposed to give you an idea on how a uniqueness proof could work, provided some certain results that I would actually therewith also pose as important open problems would be obtainable. And for this purpose, we will look into this problem here. So it's now the x derivative that is replaced by a fractional one. The y derivative just is the second one. Over here, we have q of x as a potential. It's similar boundary conditions. I have now not taken this general impedance case, but just directly boundary conditions everywhere. And here is again our overposed data. Now, we would like to proceed analogously to before. So the procedure there was to do a separation of variables by means of eigenfunctions. And now it always has to be the eigenfunctions in x direction because it's q of x, and it has to be a differential operator acting in x direction that we use. And therefore, it's now not the x Laplacian, so to say, so dxx, but it's now really our fractional derivative combined with q. So up to now, we could still go maybe with dc or raised derivative, but at this point, in order to make sure that even this eigenvalue decomposition exists, we go for a symmetric operator. And so that's why we go for the raised derivative. I'm not claiming that spectral decomposition would not exist in the DC case, but it's, well, it would probably be some more, some deeper functional analytic results that one would need there. Anyway, here we go with symmetric operator, and for sure we have a spectral decomposition just by textbook knowledge, plus completeness of eigenfunctions. Okay, now
sorry, you are muted.
Something here. Here we go. So we do our separation of variable ansatz for u, just proceeding as before. And now the ODE, the two-point boundary value problem for an ODE that w has to satisfy is an integer derivative 1. So this second derivative of w comes from this second y derivative of u up here. So, well, clearly this can even be solved explicitly. So now proceeding as before, we plug this into the left-hand boundary point in order to obtain g of y expressed by this sum, and also the derivative, the second derivative, where we can express things by means of multiplication with mu j. That's this one over here. So that's the two pieces of information that we have. Now we, of course, well, here it goes. Of course, we know the solutions of this two-point boundary value problem, and therefore we don't need also in the next step, we don't need a lemma for proving that they are linearly independent. They are clearly linearly independent, and therefore, again, we can form this dual basis in order to filter out the single items from the sum. So this gives us these identities here. And so again, we obtain both the eigenvalues and the endpoint values of the eigenfunctions. Again, under the conditions that these HAs, the coefficients of the boundary, driving boundary condition, that they are non-zero. And yes, now it would be going again for inverse Sturm-Liouville theory. However, at least when we were finished with this paper and also looking up later for preparing for talks, Sturm-Liouville theory for this problem does not yet seem to exist. Maybe someone in this distinguished audience knows more about this, and I would be really happy to learn about this. Otherwise, I would really like to pose this as an interesting problem, because if this would be true, that like before, from knowledge of spectral data in the sense of a sequence of eigenvalues and corresponding eigenfunction boundary values, that one could recover uniquely the q of x, so the potential, then we would have an analogous uniqueness result as for the previous, for the bidirection case. Okay. So what one can still obtain, just a small comment, is, so we still have this information. We can, for example, determine the fractional order from this in case it would be unknown. And that's just because we know the asymptotics of the eigenvalues. And we actually don't even need this full spectral information. We don't need the eigenvalues themselves. We just need their decay, because we can then make use of known results of eigenvalues of the fractional Laplacian, as it can be found in this paper, for example, by Kwasniewski, which tells us that, yes, basically the eigenvalues of the fractional Laplacian behave like this, up to some remainder term. If we add a potential q, as it's in our case, then also this enter just with an L infinity norm of q. So basically, the asymptotic behavior of these mu j's tells us about alpha. And so we just, of course, we can just cast this into a simple formula just by taking logarithms and just resolving for alpha here. Okay, how much time do I have left? So how much time do I have left? How long should I talk?
Well, we're quite flexible about time. I mean, if
Yes.
you can talk for approximately 1 hour, that's the plan, but it's okay if it's a bit less or a bit more.
Yes. Okay, then I will continue with a bit of analysis, and now it's about analysis of the forward problem. So we have this had these fractional PDEs or partially fractional PDEs, and of course, before going for the inverse problem, one should make sure that the forward problem is well posed. And in particular, if one goes for solving the inverse problem by Newton's method, then one would also need, on top of well-posedness of the forward problem, so well-definedness of the forward map, one would also need differentiability of the forward map, which we also showed, but it's not, I will not show it here. So just well-posedness of all types of PDEs that pop up here, including, of course, boundary conditions. So here's a small list. And so we are dealing with these 4 types of boundary value problems. So there can also be all kinds of fractional derivatives. Actually, in order to really show well-posedness with Dirichlet boundary conditions, we have to split, so to say, split the derivative into an alpha minus 1 order, and only after that doing a full derivative so that it's altogether alpha order. If we stay with this alpha derivative here, then it's more convenient at least to impose Neumann boundary conditions, but it's in the uniqueness proof, it doesn't matter because it's just, we can switch roles here, of course. So this is for either DC or race derivatives in x direction. We also have a result here with, this is with DC derivatives, in x direction. This is with race derivative in x direction. You might wonder what I'm doing in y direction. That's encapsulated in this operator A here. So A will, as we have seen it before, would just be the second derivative in y direction. But actually, this can be generalized very easily. So I have just put the general elliptic operator A here. And it can actually also could be higher dimensional. So the y direction could be, instead of just being one dimensional, it could be multidimensional. And so you see, I'm also here just writing down the boundary conditions in x direction, because this operator A that acts in y direction is supposed to come with its own boundary conditions. For example, also Dirichlet, but it could also be Neumann or impedance boundary conditions. So these were so far the fractional derivatives in x direction, but we also had fractional derivatives in y direction. That's this last problem here, the 4th one. So the x derivatives are integer, and we have a y derivative, which is fractional. And now, of course, we are somehow, since we want to take the race derivative here, we are limited to 1 dimension, which is just in the interval from 0 to L. but also equipping this one with boundary conditions in y direction, which are not written here. And actually, here for showing well-posedness, we can allow Q to depend on X and Y. Yes, that's just for the sake of the fourth problem, just in case someone wants to go ahead and pick these results and use this for their own interest, maybe not necessarily for the inverse problem. We thought it, and it was actually an easy extension to have an XY dependency of the potential here. The exponent alpha is supposed to be between 0 and 1. Well, between 1 and 2. 2 is just excluded because, of course, in case alpha equal to 2, the results are well known. Okay. Here's also just to measure, to have a space in y direction. So D is the domain in y direction, and it's a fractional Sobolev space, or more generally, it's the domain of a certain power of this A operator here. Okay, what do we need as ingredients? And so what do we have to impose on our spaces that we are using? Okay, now I have opened something up. I don't know. It's really, I'm really sorry. I have to move this bar because it always goes over my screen. And so I don't see my own slides. Okay, and then doing so, I click on things. Okay, but let's rather talk about mathematics rather than Zoom. So we are using these spaces in y direction. We need sufficient smoothness in y direction. In particular, as you can see here, we need sufficient smoothness so that this space embeds continuously into L infinity. So depending on what dimension we have on this y subspace, sigma needs to be larger than 1/2 if it's one dimension, or larger than 1 if it's 2 dimensions, and so on and so forth. So what else do we need? Actually, that actually poses the same constraint on the sigma. After all, we need to be able to employ something like this, which could be called a fractional integration by parts formula, or as it's sometimes called, Cato-Ponce or Cato-Ponce-Vega inequality, like this. This would also typically be satisfied for A being the Laplace operator, and sigma being large enough depending on the space dimension. Just the sigma that allows us to do this embedding here. Okay. And if that's what we need for the x fractional case. In the y fractional case, we can actually use the framework that is prepared, so to speak, in the y fractional case, in the x fractional case, by just replacing our Laplacian in y direction by the fractional Riesz derivative. We then just take a one-dimensional domain. Correspondingly, our h sigma dot will be, well, the sigma, that's the power to which we raise our A. And therefore, since we already have a power alpha here, it's alpha times sigma in terms of a Sobolev space. And therefore, in order to achieve at these embeddings here, we have to take alpha times sigma large enough. So large enough, since we are now really just one-dimensional in y direction, it's enough to have larger than 1/2. Also, we will assume, as mentioned previously, that our Q, it can be in some LP space. And as you see here, it's actually in some sort of, well, it's in some Bochner space. So you certainly know these Bochner spaces from the solution theory for parabolic, more generally time-dependent PDEs. Here, the role of time is taken by x. So it's a Bochner space LP with respect to the x variable, with values in this H sigma space with respect to the y variable or y variables if D is higher dimensional. And then what we will assume is that our Q, our coefficient, it's supposed to be just in this space. And so there needs to be a bit of regularity in y direction. The regularity in x direction can actually be quite low. So we could go for p equal to 2, and as in the setting we had before, our q of x would be the L2 function, but it should be sufficiently close, that's what it says here, to a non-negative L infinity function. Okay. And then the outcome of the analysis is using these tools that are on the previous slides, basically, is that we have well-postedness of all these 4 different boundary value problems. And again, the solution space will be a Bochner space with x taking the role of time, so to speak. And for example, here, it's also the expected regularity here. Yes, we have h alpha over 2 with values in h sigma. So that's actually the statement for the y fraction, for the x fractional cases. Sorry, I did not put the last one here. This would be the typical regularity setting for the x fractional case. So we have alpha over 2 in space, and then sigma in y direction, in x space and in y space. And yes, and if we just go down for just, so to say, 0 regularity with respect to x, then we can achieve at 2 plus sigma regularity that is inherited from the source term f over here, so to speak. Okay, now I have another small section which I'm of course happy to talk about now. And that's going back to the inverse problem. So I mentioned already we solved the inverse problem numerically using Newton's method, but actually it was some sort of extended version of Newton's method, and it was actually making use of an extension of the q of the potential. So we write the forward operator like this. And we first of all start off in order to enhance, so to speak, the possibilities of proving convergence. We enlarge the space in which we search for our potential. So really also here, we not just go for a q of x, but we go for a q that can depend on x and y. So the function space in which q lives, that's this x space here, L2 with respect to x, and h sigma with respect to y. So we have a q that depends on x and y. So the image space is the space where we measure our boundary data, our Neumann boundary data, g of y. So it's a y space. D is our y domain. And this would be our data space. Okay, that's not the full answer, because of course, if we take this full general Q here, we will not have a chance to uniquely determine this from just these y-dependent boundary conditions. And therefore, in our inverse problem formulation, sorry, I have it on the next slide, we will also add a term that penalizes this y dependence. So after all, we want to recover a q that depends only on x. Originally, we allow, so to say, our inversion algorithm to search for the q in a larger space, but we will restrict it by penalization successively during the Newton iterations to lie in the space of q functions that only depend on x. First of all, with this forward operator, with the extended one can show that this f satisfies a so-called range invariance condition. This now goes a bit into regularization theory for iterative methods for nonlinear inverse problems. Newton-type methods can be proven to converge there only under some certain structural assumptions on the forward operator. And one of these structural assumptions would be range invariance. So why is it called range invariance? It's an assumption actually on the derivative. And it tells us here that the derivative at some point q tilde can be written as the derivative at some point q0 with some regular invertible and boundedly invertible operator R. Actually, this operator R is not that far away from the identity even. So this clearly tells us, yes, that's why it's called range invariance, that the range of f prime of q tilde is the same as the range of the f prime of q0, because this R here, due to the smallness condition, will just be an isomorphism, at least locally, around the exact solution. So one can actually explicitly write down what this R operator here will be. I have written it down, so to say, for your information. It really exists. And then one can go into the theorems about Newton's method for ill-posed problems, regularized Newton's method for ill-posed problem, and conclude that one gets convergence. So how does such a regularized Newton method look? What does it look like? So we would go for, so it's Newton's method, so we linearize the problem. And instead of solving it exactly, due to the ill-postedness of the original problem, also the linearization will be ill-posed. So we solve it in a regularized way. And so what you see here is basically Tikhonov regularization. So we add a regularization term that takes care of the ill-postedness, and that penalizes deviation of q from some initial guess q0. Could be a constant, for example. Additionally, we have this p term here. So p is the penalization term that I talked about before. That's the term that penalizes deviation of q, which is first of all a function of x and y, from its mean value, which only depends on x. So we take the mean, the average with respect to y here. And so if this object here under the integral, if it's 0, then clearly q will not depend on y, because q will be something which only depends on x here. So we penalize the L2 norm deviation here, and this gives a penalty that can really guarantee, this is also something which we can show, that as we solve these, as we do these Newton iterations, and as we properly choose the regularization parameters gamma n, as n tends to infinity in the noiseless case, or as delta tends to 0, so the noise level tends to 0 in the noisy case, but then we have to stop on time to get a regularization method. This really gives us convergence of these reconstructions that we obtain by Newton's iteration to the true q of x potential. That's what this theorem here says. So up here, there's the method. That's what we really have implemented. Up here, that's this range invariance condition, which was the important condition that was needed to verify in order to conclude this convergence here. And here's the convergence result. So q dagger is the true q of x, the potential that we want to reconstruct. With this, let me thank you very much for your attention.
Thank you very much for the presentation. Do we have any questions or comments from the audience?
I see there's something in the chat. Okay. That's great. I got a hint on fractional Sturm-Liouville problems.
I'm also putting a message in the chat. So yeah,
yes.
Pavan and I shared a
Yes,
bunch
I
of
think
papers.
this one I know. This one I know, yes. Yes, Margot Shatter Klimek. I think I know this one too. Yes.
Yeah, I guess
Yes,
probably you
of
would know
course.
them because they come up with
Yes, she's a very
Sturm-Liouville.
well-known person in this topic, and also of course also her co-authors. But let me check again. Maybe I did not have look into all of these papers, but still, it's good for me to learn about this. I have to find out how to extract all these references. But yes,
Send
now
them
of
to you
course
by
it should be
email.
you to thanks a lot. That's great.
Yeah, I think that's
So
the easiest
probably,
thing.
yeah. So probably, Arran, what you could do is like when you send out the YouTube links, you can collect all of these references and send it out. So
Yeah.
that would be nice. And also note that Professor Lu+qu also has some little theory on general fractional calculus. I've not read the paper, but I've seen the title because I didn't find the time. I did not find the time to it. So so maybe Aaron, when you're sending out that email, probably you can collect that reference too.
Okay.
Yeah.
This would be great. Yes, thanks a
Yeah.
lot. Yes, of
Yeah,
course,
yeah,
you
yeah.
would also be a person to ask about this.
Yeah.
But I would expect that Bill has asked him this problem, this question, because Bill Randell, he has been already previously looking into this Sturm-Liouville
Yeah.
problem in more detail together with Pranjivan, actually.
Yeah, and also on the numerical side for inverse problems, we had some work when I was at Brown. I can send you that references too. I think I've added here, but I have to include one more reference. So what we were doing was like trying to identify the fractional order given the data. So we had a numerical methods algorithm in it. So we call it fractional pins. We call it
Yes,
fractional.
of course. There's also methods. Well, of course, it's when it goes about identifying the order. I should have mentioned Masahiro Yamamoto, who gave his talk,
Yeah.
I think 2 weeks ago, who did this pioneering work on identifying the order. So
Yeah.
he just came out sort of it as a byproduct product. But if you look at the
Yeah.
formula, it looks a bit similar to his formula that he usually gets.
Yeah,
For
yeah,
good reasons, of
but
course.
the papers I was mentioning, it's
Yes.
purely computational work. We don't really have any theory. I mean, to build the complete
Yes.
theory, to build the complete theory, one of the missing questions right now is that on neural networks, what is the guarantee of convergence? I mean, there is one theoretical guarantee for convergence for neural networks, which was Chen and Chen paper, but that does not give you any indication of like if you make your network big or small, what's going to happen. So that's kind of a bit of a weak result. So mathematical theory on that part is now an active topic. So hence when you implement neural networks with fractional operators, the theory is largely missing. But it's nice to see, like, all right, in the classical setting there is something. So the papers I was mentioning is purely computational work, and yeah.
Okay, thanks a lot for mentioning. Yes,
Yes.
it's also nice to that open problems, interesting open problems are mentioned in this seminar, I think.
Yeah, we did it for like the case of turbulence, like identifying fractional orders, which were variable orders in my case. So, but that paper is long, but in any case, if you have any questions, we can also take a Zoom meeting and I can explain you how
Okay, great. Thanks a
how
lot.
it works, how it works. Yeah. All right, from my side, thank you.
Thank you, Pavan. I've also copied the messages from the chat into a text file just in case they will be lost when the meeting ends. If anyone else wants to contribute, like knows some relevant papers, please post them in the chat as well, and I can share them by email with everyone. Or if anyone has any question or comment, you can unmute and ask.
Hello,
Yes.
I have a question. Barbara, thank you for nice presentation. So in the experiments in the beginning, you showed Q was 0 on the boundary. So we were looking for Q of X, and in this on these graphs, exact Q was 0 on the boundary. Have you considered also experiments where potential is non-zero? So here in -1 and 1, the value of Q is 0. Oh, you are muted.
Sorry.
No,
Okay.
it's fine.
No, I don't remember. To be honest, I don't remember whether we tried this.
And like update in the Newton scheme.
Whether it makes a difference.
Yeah.
It could make a difference because it could make a difference in the convergence speed. Because usually when we look into inverse problems and want to prove convergence rates, we would impose these source-wise representation conditions. And then it means, for example, one of these would be that the coefficient that we want to reconstruct should be in the range of the adjoint of the linearized forward operator. And if the forward operator and this linearization comes with boundary conditions, then this adjoint also comes with boundary conditions. And this quite often imposes boundary conditions, which are then needed in order to get a certain convergence speed. The conversion itself still happens, but it happens possibly slowly, and this could be visible if it would be like that the source condition implies boundary conditions could be visible in a slower convergence on the boundary at the boundary points.
Yes, okay, thank you. I was wondering about that. And something I don't well understand is the uniqueness proof. Because there's a condition which depends on the eigenfunctions, but the eigenfunctions depend on Q as well, and Q is unknown, so how
Yes,
can
but we
you
don't
check
know,
this?
we don't assume that we know the eigenfunctions. It's really just that and it's actually also the information that we get out is only sort of partial information on the spectrum. So after doing all these elimination steps, let me see. Yes, that was this uniqueness, the really uniqueness proof. After all these manipulations, what we get is, as an information, that's the thing down here, right? So these sort of combinations so of course from these two items we can separate out, given that Aj is non-zero, we can separate out the mu j and the psi j prime of 0. Just that, not the whole function. And that's this spectral information that we need, and that's enough actually in case the derivative is an integer one in x direction. That's enough in order to really recover the Q. So that's this result here.
This
yes.
is 382 theorem.
Yes. So the psi's and the mu's are not known. So after all, the mu's become known, but the psi's are not. And therefore we only have, so as it's typical for these inverse spectral problems, so in the Sturm-Liouville problems, one has this differential operator, one wants to recover coefficients inside, for example, such a potential here. And then one has some certain spectral information on this operator here. And from this, one can really recover the Q of X. And in our case, it would be this one.
Okay, thank you for the explanation.
You're welcome. Thank you for asking.
Thank you for very interesting talk. You see, here you see, using this theorem 3.8.2, you can recover Q, but actually you cannot recover. You can only show that unique Q is
It's not constructive. It's not constructive at all, I would say.
To recover, you should,
yes.
I mean, it doesn't give existence.
Existence is assumed.
It doesn't give existence.
Okay, you're asking about existence. No, existence is assumed because we assume that
but
our
this
model
this
gives
doesn't give
reality.
existence.
Yes.
It's only for uniqueness.
Yes. Yes, I completely agree. But
So
for
that
solving,
once you don't have existence, you cannot recover it.
But we are in inverse problems, we are not interested. Well, I shouldn't pose it. It's maybe too blunt to pose it. We are not interested in existence because we assume that what we are looking for exists. The important question from the inverse problems point of view is whether we can really uniquely determine these quantities. In our case, the Q. And so the point of view for us is not like in PDEs, for example, where one wants to really also have existence, and which is actually we have in our well-posedness for the forward problem. But here we really are after the uniqueness.
Yeah, thank you.
So thank you very much for pointing to this.
Can I ask some questions?
Yes, of course, you're welcome.
Thank you for your great presentation. I'm going to ask you, did you use some other type of general fractional derivative on your work?
No, not yet. So this, I think, would also be an interesting topic to look into, especially probably in this audience, to look at what changes, how the problem changes if instead of these just simple and meanwhile also quite classical DC and race derivatives, if one uses some sort of generalized fractional derivative here, or even if we think about, for example, y being the y direction being higher dimensional, as we had it in our well-posed forward proof, if this would be, for example, some sort of fractional Laplacian or something like this, or some other way of some other type of fractional derivative.
Thank you for your answer.
You're very welcome.
And can I ask another question?
Yes.
Did you use the another type of fractional derivative on your boundary conditions?
On the bound? No, on the
on
boundary.
other works.
You mean on the boundary conditions?
As in a fractional boundary condition instead of an ordinary derivative, you mean?
Yeah.
Is this? No, we didn't do this yet. This is also something which might be interesting to explore for sure.
Thank you.
So we here just focused on we try being aware at least of the, well, of course my co-author being much more aware than myself, but being aware of the fact that there's so many types of fractional derivatives and of ways to use them here. We tried just to get a first step into this problem and to get an impression on how it influences the inverse problem. We just looked into, well, putting here derivatives separately for x and y, putting them to fractional ones, and also a certain small selections of the derivatives. So one-sided, because we expected that this would influence the ill-postness, as we have also seen in the reconstructions and the singular values. And on the other hand, the symmetric ones, because this allows us to some extent, at least for one of our uniqueness proof, to use the spectral, the spectral theorem basically for the separation of variables approach.
Understand. Thank you very much.
Thank you.
I have a question, please.
Yes.
Yes.
Thank you, Prof. Barbara, for your interesting talk. I have one question, just a general question about you obtained the series solution and the uniqueness was proved, and also convergence of the potential. So my question is whether the convergence of the series arise or the convergence of potential leads to the convergence of that series solution.
So convergence of the potential in the sense that
the convergence of inverse problem, you proved it.
Of the so that's sort of separate results.
Separate.
Because here we did the uniqueness proof, the other proof about convergence of Newton's method. This was well, one part at one point we also need some injectivity, which I did not show explicitly here, but basically it's different things.
Okay, because in the first problem you considered a series solution in terms of psi and w.
Yes.
Then you proved existence in uniqueness. My question is whether the question of the convergence of that series solution arise or not in this problem.
The question, of course, it arises, but it can be settled by arguing that we have a complete system of a complete eigensystem, and therefore yes, the solution can be expanded in that eigensystem. That's what is done here. For each single point y, so to speak, we can expand the solution as a linear combination, so to say, infinite linear combination of the psi j's. And then this gives us, this will give convergence with respect to x of this sum for j from 1 to infinity. Yes, it's basically that argument.
Yeah, thank you so much.
Thank you.
Thank you. I actually had one question. Sorry, I know we're taking your time a lot with many questions, but it was related to the question of Schochterbeck, the one before last. Because when you started, you showed firstly the non-fractional problem with the classical Laplacian. And then I was expecting on the next slide to see the fractional Laplacian. And instead, which is very interesting to me, you're making it fractional only in one dimension, either x fractional or y fractional. Can you explain sort of intuitively the reason, either physical reason or mathematical reason, why you did only one dimension fractional?
There are several reasons. Let me start with the the fractional Laplacian is a non-local operator, not only in the sense of being non-local inside the domain, but sort of also outside. And so it would, first of all, not have been clear on what it means to impose Dirichlet and Neumann boundary conditions, what it would mean to measure Neumann boundary conditions in the context of a fractional Laplace operator. That's the first reason. The second reason was thinking we were really intending to think in directions, yes, because in our intuition, since we want to recover a function that depends on x and we measure in y direction, it should make a difference on in which direction we have the fractional derivative, in which direction we have non-locality. So in this sense, it would be, we were really after a sort of anisotropic type of fractionality in the derivative, which would not have been immediate in the fractional Laplacian. I mean, one could do it, but that's the two main reasons. And the third reason is that while we have been doing something on time fractional derivatives and also looking into several inverse problems on that, our experience with our own experience with really not only reading but also publishing with fractional Laplacians was limited, to put it in a friendly way. And so we said there are other experts who look at, actually they look into the fractional Schrödinger equation. That's an interesting problem where you have q of x and y, so dependence of q on all variables that appear here, and also in a general domain, and also with a general Laplacian up here. But then clearly you would need measurements, not just one single additional measurement on the boundary, but you would need something like the Dirichlet-Neumann map. And of course, there's clearly a community doing things like this. And there's things that are well known there, but the way the problems are posed there is different, because already the type of measurements is different. And so it's just a different way of a different problem that we are looking. Of course, there's related problems with the fractional Laplacian, I should say, but it's we wanted to put a different emphasis here.
Yeah, that makes sense. Thank you. I wonder though, there are other ways of doing, let's say, fractional in both dimensions that would not involve the fractional Laplacian. For example, you could take fractional Riemann-Liouville with respect to x and y separately, or other types of two-dimensional
operators. Of course. And it would be interesting to look into this. So it was really, so these were really just some sort of spot-on examples with this dc derivative and also with the race derivative. But of course, there's many ways to and also so we did do some numerical experiments where we put separately fractional derivatives, but that's certainly not what you mean here. Yes, it would be really to have another way of doing it in a two-dimensional way or high-dimensional way, but anisotropically in the different directions.
Yeah, so there are other types of two-dimensional operators, for example, with some kind of kernel function which entwines both dimensions. So you cannot separate x and y, but it's still fractional with respect to both x and y, and it could be on a finite rectangle. I don't know if you remember the talks in Kent.
Of course, I remember this from your talk in Kent, yes.
Yeah, yeah. So
yes, and at that
ideas could
point
be
I
combined
thought
here.
this could be really worthwhile looking into for problems like this.
If I may add one remark, I mean, such equations, in my understanding, are actually of very interesting cases, because you, in the x and the y direction, to have different fractional orders. So there is a work on turbulence, which is my work. I have considered orders which are in the x direction is different from the y direction and from the z direction. And the first work was fractional runs, which is with the paper 4 in here, but I also have fractional Navier strokes, where you have a transport and diffusion term, time term, which there are like 4 fractional orders in 3 in space, which are different from each other, and the 4th one in time. So these cases are actually very practical, and
yes, I would expect that one needs it for modeling.
Yes, it does, because turbulence is very an isotropic field, so you need different orders in every direction.
All right. Do we have any other comments, questions? Then thank you very much for your time, for the talk, and for engaging in discussion afterwards.
Thank you very much for the nice discussion and for coming, of course. And of course, also for having me in this lecture series.